Hello and welcome to our lesson on unit vectors and the dot product. So the focal point for the lesson today is going to be the dot product, but this is a concept I wanted to build in the unit vectors. This is a concept I wanted to build into the previous two topics. I just didn't have time. So I'm going to do a little intro into what we call unit vectors, and then we'll focus on, again, the important stuff, the fun stuff, which is going to be our dot product. So a unit vector is just going to give us some new notation, and hopefully it will help you when you go on to your higher levels of mathematics, or even if you're working in physics, because this is notation that's used there a little more often. We're not going to do a lot with it. I just, again, want to introduce this concept to you. So a unit vector is a vector that has a magnitude of 1 unit, so hopefully that makes sense. And there are really two of them that are important for us to define here. So one is going to be the horizontal vector that has a magnitude of 1. We're going to call that I. So I is going to be defined as, again, a horizontal vector with a magnitude of 1. That means we go 1 in the horizontal, but we do not move in the vertical. So that's defined for us as I. And then we're going to define j as a vertical vector with a magnitude of 1. So that means we're not going to move horizontally, we're just going to go vertically 1 unit. So that's defined as 0, 1. So graphically, what does I look like? Again, that is a horizontal vector with a magnitude of 1. So that is what I looks like. And then what does j look like? That is a vertical vector with a magnitude of 1. So that is what j looks like as a vector. All right, so again, we're going to call this j, and we're going to call this I. So what we can do is apply this I and j form to our component vectors. So let me show you how it looks here. Let's say I drew a vector into this picture, and I'm going to have it land, how about here? So if I put this vector in, that was pretty close enough. So this vector, I'm going to call it u. In component form, we would say, because it ends at 2, 4, or from start to end, we have to go right 2 units and up 4 units, the component form would be 2, 4. Now in terms of our unit vectors, that means I'm going 2 of those unit vectors along the horizontal axis, and I'm going 1, 2, 3, 4 of those unit vectors along the vertical axis. So this vertical distance here is like 4 of the j's that we defined over there, and this horizontal distance is like 2 of the i's that we defined over there. So another way to describe this vector, again, is in what we call ij form. We could say that u is equal to 2I plus 4j. Okay, so just a new notation. So I can just give you the component form, give you the vertical and horizontal displacements, or I can give them to you in terms of I and j. Now you'll notice, because our I and j are 1, whatever these units are, when we multiply by that factor of 1, we're not going to change those values. So whatever those values are, those are the values that you're going to see here. We're just putting a factor of I and j in there, and then adding in the plus sign in between. So again, that's called the ij form of our vector. So more generically, if we have vector u being equal to ab, again, that would be the endpoint for that vector, the component form of that vector, the ij form of that vector would be u equals a times I plus b times j. So you have this multiplied by I, and you have this multiplied by j. And then a plus sign in between. Again, that's just an ij form of your vector. And this is used a lot, again, when you go to physics and some higher levels of calculus. But I just want to introduce it to you here. So not a tough concept, but just new notation. Alright, so let's try to go back and forth. If I gave you a normal component form like negative 5, 8, understand that if I said negative 5i plus 8j, it's the same thing. It's negative 5 of the horizontal ones and 8 of the vertical j's. Or here again, this would be the same thing as 6i and then a negative 3 j. That would be the ij form, or in the form ai plus bj. Okay? Or the vector operations that we talked about before, those would still apply. So recognize that this negative 1 in front of the I and positive 2 in front of the j means this vector could also be written as negative 1 and positive 2. So when I go to find 2u, in the same way I would just multiply by 2, I could just multiply each of these by 2. Alright, so the same operations we could apply to either form, but I'm going to leave them in this form. So 2 times u would be 2 times the negative 1 plus 2j, and then I'm going to add 3 times v, which over here is not negative 1. I can't even read. This is negative I plus 2j, and then 3 times v, which is I minus j. So again, the same way I can just multiply in the components, I'm multiplying here. I'm just multiplying the coefficients of I and j, which are the components of my component form. So when I multiply, this is a negative 2i, and then this is going to be a positive 4j, and then here I have a positive 3i, and then here I have a negative 3j, and again I can add the corresponding components. So I put these together, which would give me 1i, and I can put these together, and 4 minus 3 leaves me also 1j. So I plus j would be the result of 2u plus 3v. And then again, understand that that's the same thing as 1i and 1j, so 1, 1 in component form. So same thing, okay? Just two different ways to write it, two different ways to go through the operations, but new notation, okay? And that's really all we're going to do with that. The fun part of what we're going to do is talk about this dot product. So what is the dot product? It's basically another operation. Okay, the dot product is an operation that we're going to be performing on two vectors, but it is distinct from the other operations. All of the operations we've seen with vectors so far produce other vectors. So if I say take a vector and double it, then I have another vector that is doubled in magnitude. Or if I said take these two vectors and add them, then I have a new vector that is the sum of those two vectors, right? This operation, this dot product operation, doesn't produce a vector. It produces a real number, which we're going to call a scalar, right? It produces some real number, so we get an actual numeric value instead of a vector. Because that happens, we sometimes call our dot product the scalar product. And then there's another vector operation called an outer product, which is a bit similar, but we want to distinguish between those two, this dot product and that outer product. So sometimes we call this one the inner product, so the inner product being different from later you might see something called an outer product. We're not going to do that, but just for reference, there's some other names for our dot product. Okay, and I'm going to show you what it is in a second, but just so you understand why these are useful. What we're going to do with the dot product after we practice making basic calculations is we're going to use it to determine angles between vectors. That's the key here. Find an angle between two vectors, which we've done before, but we saw that could be a pretty complicated process. We can also use it to derive some geometric theorems, and when I say we, not us, but it could be used to do that, and it also is very useful in solving physics problems. Again, not something we have to do, but something that can be done. So we're going to focus on that first version. Now again, what is the dot product? So if I give you two vectors, let's just say u and v, the dot product, which will look like this, u dot v, that's how we would read that, not u times v, we're going to say u dot v so that we're clear we're finding something called the dot product, incorporates addition and multiplication. So dot product says u dot v is going to be equal to a product of the horizontal components. So we have a times c, and we have another product of the vertical components. We have b times d, and then in between, what we want to do is add, oops, sorry, my paper jumped. We want to add those two products. So we're putting in some multiplication and addition into this dot product. But again, the result is going to be a scalar. It's going to be some real number. So u dot v multiply the horizontal components, multiply the vertical components, add those two products. That is your dot product. Okay, so let's practice making the calculation a couple times, and then I'll show you how we can use this to find angles between vectors. So here, if I multiply, or if I want to find my dot product, I'm just going to, for the sake of practicing with notation, I'm going to call this u and I'm going to call this v. So u dot v would be found by multiplying the horizontal components, so negative 5 times 3, plus we're going to multiply the vertical components, the 2 times the negative 1. So a pretty easy calculation. U dot v ends up being negative 15 minus 2, which in this case makes it a negative 17. Okay, simple enough. Let's try it again. Right, just multiplying and adding, that's something we can all handle. So again, I'm going to just call this u and v. So u dot v is going to be equal to negative 5 gets multiplied by 2, and 2 gets multiplied by 5, and we want to add those two products. So that's a negative 10 here and a positive 10 here, which means our dot product in this case ends up being a 0. And then here, multiplying the same thing by itself, the same vector by itself, we're going to get something that makes sense. So again, I'm going to call this u and v. So u dot v is going to be negative 5 multiplied by negative 5. So negative 5 multiplied by negative 5 plus, we're going to multiply the 2 and the 2. And so we have a positive 25 and a positive 4, which makes our dot product here have a scalar real number value of 29. And then I got one more, which I see my vector is given in this ij form, but it works the same way. If it's helpful, you can maybe rewrite this. 4i means we have 4 in the horizontal component, and since there isn't anything listed for j there, that would be 0 in the vertical component. And then here we have 5 in the horizontal and negative 9 in the vertical. So those are our two vectors in the other form, if it's easier for you to see it there. So when we go to find our dot product, again, I'm going to call this u and I'll call this v. So I'm going to say u dot v is going to be equal to, we're going to multiply 4 with 5. So 4 times 5 plus, we're going to multiply the 0 and negative 9. And that's a nice product because that goes away. So it's just 20 plus 0, which is 20. So dot product ends up being 20 on this last one. Okay, so not so bad. So that is one small calculation that can be made in the process of finding an angle between two vectors. Before I can show you how we can do that, I gotta connect this dot product and something we've talked about before, which is our law of cosine. So we're going to look at a geometric interpretation of the dot product. Now this hopefully is a picture that is looking familiar. If I wanted a formula to relate the three sides of an oblique triangle and some angle in that triangle, this version of the law of cosines would relate those pieces. Now what I want to do is directly connect this to, instead of a triangle with side lengths A, B, and C, what if I have a triangle that's created by vectors, where I replace my A, B, and C with those vector lengths, and I replace my angle with some direction angle. Okay, so instead of A, I have this vector with the length, magnitude of u. Instead of C, I have this vector with a magnitude of v. And then instead of B, I have this vector with a magnitude of u minus v. Now, some of you might be thinking to yourselves, why? Why is this vector called u minus v? That is not arbitrary. Now, I don't think we did any geometric differences. Let me just show you really quickly what's going on with that difference. Let's say I had a vector like, I don't know, at 3, 4, and I said to subtract a vector at, let's say, 2, 1. Okay, that landed there. If I said subtract those, we know algebraically this is pretty easy. We subtract here, 3 minus 2 would leave us 1, and we subtract here, the 4 minus the 1 would leave us 3. So this would be the difference, right, between those two vectors. So, how does this look graphically? Let me show you, and then this will make sense what I put on the other picture. So let's go 1, 2, 3, 2, 3, 4. So I'm going to put this vector in first. I'm going to call this one u. U lands at 3, 4, so here. Alright, so here's my vector u. And then I'm going to call this one v. So my vector 2, 1 is going to land here. So here's my vector v. Okay, and actually, let me move this v. It's going to get in my way. I'm going to put v over here. And now this is going to bother me, so now I'm going to put u over here. Okay, so there's u and there's v. I said if I found the difference between those, that difference would be this vector here. Now, in the picture I showed you, go back to this for a second, I said that that difference should be represented by the third side in the triangle that I could make, right? If I connected the head of vector u with the head of vector v, that should represent the difference. So let me go back. If I did that here, if I connected the head of vector u with v, so if I started here at v and I went here to u and made a third vector, what would the component form of that vector be? Well, if I have to start here and end here, I have to go over 1 unit and I have to go up 3 units. So that component form would be 1, 3. So this vector is in fact the difference of my two vectors. Okay? So it's showing me the difference between the difference between the y components and then the difference between the x components, which is exactly what we did algebraically. So hopefully it makes sense that this third side of the triangle is the difference between those two vectors. Okay? So now that that's hopefully a little more clear, what I want to do is basically plug all this information into my law of cosines. So I'm going to replace my side lengths a, b, and c with now magnitudes of vectors u, v, and u minus v, and replace my angle b with my direction angle theta. Okay? And watch what happens. It's the magic. This is where the magic happens. Okay? So plugging my vectors and direction angle into my law of cosines. Because I do still represent a triangle, right? So in place of side b, I have this vector, which is the difference of u and v. Now, that vector, remember, has a magnitude. It's not just a side length anymore. So instead of b squared, I'm going to say the vector u minus v, that magnitude is going to be squared. And it's going to equal, instead of a squared, it's going to be this vector, its magnitude of u that has to be squared. So the magnitude of u squared. And then I have c squared, so that's v. And again, it's a vector, so it's the magnitude of v squared. And then I have minus 2 times, again, instead of a and c, it's going to be the magnitude of u and the magnitude of v. And then at the end, cosine of in place of v, theta. So when I plug all this into my law of cosines, it looks like this. You're thinking to yourself, like, what? This isn't helpful at all. What is she doing? But I'm going to show you the magic. It's going to happen. Just give me a second. So first, let me work on this. If I have just u minus v, let's ignore that magnitude for a second, and I was to square that, that means u minus v has to be multiplied by itself, u minus v times u minus v, and I get a u squared, and I get a negative uv, and here I get another negative uv, and then I get this positive v squared. So I end up with u squared minus 2 times uv, and then I end up with this v squared. Okay, so back to where I was up here. When I simplify this, I have this u squared, but remember, it's not really just u, it's the magnitude of u squared, and then minus 2 u dot v, I'm going to leave in there because u dot v is my dot product, and I want to be able to show you how this connects. So instead of throwing the magnitude in there, I'm going to leave that as a dot product between those two vectors. And then v squared, remember it's not just v squared, it's the magnitude of v squared. So that's what I have now in place of this, is this, okay? On the other side of the equation, I still have magnitude of u squared, magnitude of v squared, minus 2, magnitude of u, magnitude of v, cosine of theta. But if we go to clean this up, lots of things are going to happen. So let's say I wanted to move this magnitude of u squared over, I would subtract it. Well, since I have that same term on this side, those are going to cancel. And the same thing happens with the magnitude of v. If I go to subtract this over to the other side, since I have the same thing on the other side, those are going to cancel. And then here, I have a negative 2. Let's say I wanted to divide that negative 2 over, since that looks the same on both sides. If I, let me change it to another color. How about pink? Because this is, maybe it's too many steps in one. Let me rewrite what I have right now. I have negative 2 u dot v equal to negative 2 magnitude of u, magnitude of v, cosine of theta. Well, if I see a negative 2 on both sides, again, I could divide that out. Divide this side by negative 2, divide this side by negative 2, and now I have another definition for my dot product, right? So this says that u dot v, my dot product, is also going to be equal to the magnitude of u times the magnitude of v multiplied by the cosine of theta. Now you're probably thinking, I don't know what that means. Does it mean anything to me? How is that any more helpful than the other dot product? Well, that dot product now is connecting some things that we want to know. Like, I know how to calculate a dot product. That dot product is easy to calculate. And if I knew the magnitude of u and the magnitude of v, which sometimes I know, and I wanted to figure out the measure of the angle in between those two vectors, this formula could help me do that. Okay? And maybe it's not 100% clear yet, but we're going to get there. So this place where we ended, this is another formula, accepted formula for our dot product. We actually, in fact, call it the dot product theorem. That's what I see in this, or what I have in this box here. Right? If we have some angle that's between two non-zero vectors, u and v, that's what I showed you in the picture, and that angle does have to be between 0 and 180, then again, this is another version of our dot product formula. But again, to make this even more clear, if I wanted to solve for the angle, let's just say the cosine of the angle, it's being multiplied by these two magnitudes. So I could divide them over and give another version of this formula. So this leads me to say that the cosine of my angle would be equal to u dot v divided by the magnitude of u and the magnitude of v. Right? And this one looks even better. But I'm going to go one step further. If I want to be able to find the angle that's between my two vectors, figure out what this angle is without having to go to my law of cosines every single time, right? If I want to find this angle, I just need to get rid of the cosine, and I can do that with inverse cosine. So this leads me to saying the angle is going to be equal to the inverse cosine of, again, u dot v over the magnitude of u times the magnitude of v. So if I want to find the angle between two vectors, I can take the inverse cosine of that fraction that contains the dot product in the numerator and the product of the magnitudes in the denominator. So again, I'm going to put a lot of words in here, but this is the angle between vectors equal to the inverse cosine of this fraction. And in this fraction, I have in the numerator the dot product, and in the denominator the product of the magnitudes. That is so much easier to calculate than all of the law of sines and or law of cosines and then maybe law of sines work that we were doing to find the angle before. Okay, we actually did one on the homework. I showed you one on the warm-up. if you were in class. So let me show you now how much easier this will be, and maybe you're not going to like it, but I think this is much easier than the work we were doing with the law of cosines. Now, you see how this came from the law of cosines, but it all cleans up with our dot product. So if I said to find the angle between these two vectors, if I wanted to use the law of cosines, it wouldn't be enough information. I'd have to find the I'd have to have more information, because remember, we need 3 components to guarantee a triangle before I could apply law of cosines or law of sines. So with these two vectors, not enough information. I could get magnitudes, right? But I don't have any angles. So let me my paper is frozen. Let me just freeze here for a second. Okay, I'm back. We glitched. All right. So if I want to find the angle between these vectors, this is the formula that I want to focus on. Okay, that angle between my vectors is going to be the inverse cosine of the dot product over the product of the magnitudes. Now, the dot product, easy because I have my 2 vectors, but the magnitudes I don't directly have here. Now, do you remember how to find the magnitudes? So that's a concept we talked about in the previous topic. Maybe I have this here actually, so I can reference this. If I want to find the magnitude of, yeah. So if I wanted to find the magnitude of a vector, right, I know where it's landing. That landing place, 3, -2, that gives me my vertical and horizontal components. Remember, that magnitude is the third side of the triangle. It's the hypotenuse of the triangle, and so I can use Pythagorean theorem. So we talked about this formula yesterday. The magnitude of our vector is the square root of the sum of the squares of our components. Okay, so that's what I'm doing here first. Where am I at? This guy. So if I wanted to find the magnitude of u, it would be the square root of 3 squared plus 1 squared. So 3 squared is 9, 1 squared is 1. That means that the magnitude of u is going to be the square root of 10. And similarly here, if I wanted to find the magnitude of v, that would be like the hypotenuse in the triangle that's created with side lengths of 2 and side lengths of 5, right? So this is going to be the square root of 2 squared and 5 squared. So the magnitude of v is going to be the square root of 2 squared is 4, 5 squared is 25, 4 and 25 makes 29. Okay? So I need to know those magnitudes because they're going to be multiplied on the bottom of my fraction. And then I need my dot product, which is pretty easy to find. So let's do that. If I wanted to find my dot product, if I wanted to do, oh, come on, paper. U dot v, I'm going to multiply my horizontal components. So that's going to be 3 times 2 plus, I'm going to multiply my vertical components. So 1 times 5. And I end up with 3 times 2 is 6, 1 times 5 is 5, and 6 plus 5 makes 11. Now I have all the information I need to find my angle. So the new version of the formula I said is going to be that the angle is going to be equal to the inverse cosine of a fraction. And in that fraction, the numerator is the dot product, and the denominator is the product of the magnitudes. So in the numerator, my dot product of 11. In the denominator, the product of my magnitudes, which would be, actually, let me color code this. So in my numerator, 11. In my denominator, my product of my magnitudes were radical 10, and then that's going to get multiplied by the other magnitude, which is a radical 29. And then just, if I wanted the exact form, which I don't even know why that would be helpful, but this is something we're going to want to approximate anyway. The exact form, I suppose we could do this, would be inverse cosine of, so this would be 11 over radical 290. Who wants to, can we even simplify 290? Nope, because 29 is prime, 10 is 2 and 5, nothing's going to come out of that, but we could definitely rationalize, and this is probably not necessary. So inverse cosine of 11 radical 290 over 290. That would be the exact value for our angle. But again, ultimately, we're going to want to approximate this. So with the calculator, we say, hey calculator, what is the inverse cosine of a fraction that has, and I'm going to put the unrationalized version in there just in the event that I messed something up. So 11 over, let me put in radical 10 multiplied by radical 29, and then just make sure I'm in degree mode. So I get about 46.98, 46.98 degrees. And that's going to be my angle. Okay, so if we can calculate those two magnitudes and that dot product, the inverse cosine of a fraction containing those things is going to get us that angle. To me, easier than the law of cosines, but maybe you're thinking, okay, this is just as terrible. Let's try another one. So if I want to find the magnitude of u first, so that's going to be the square root of 2 squared and negative 6 squared. 2 squared is 4, negative 6 squared is 36. 36 and 4 makes 40, and then v, magnitude of, that's u, v is going to be the square root of 6 squared and 2 squared, which is the same, 36 and 4, so the magnitude of v is the same, radical 40. And then my dot product, u dot v, is going to be 2 times 6 added to negative 6 times 2. So that's a 12 and a negative 12, which means our dot product is going to be a 0. Okay, so that actually makes this one even easier. So my formula says my angle will be the inverse cosine of that dot product on the top and then the product of my magnitudes in the bottom. But it doesn't even matter what's in the bottom because if the top is 0, we're just looking for an angle such that the cosine of our angle is 0. Now the calculator is going to give this to you, but you shouldn't need the calculator for this. Oops, almost put the answer in. It's 90 degrees, right? At a 90-degree angle is where we have a cosine of 0. So here we end up with a nice 90-degree angle. And then just, again, to throw some terminology in here, if these two vectors, here's what this is saying. We've got some vector u, we have some vector v. This is saying the angle between them is what we just found, right? In this case, it's 90 degrees. If it's 90 degrees, it means those vectors are actually going to be perpendicular to one another. So if the angle between, this means, pick another color. Okay, the vectors are perpendicular to one another. Can't spell. Perpendicular to one another. And then we have a symbol for perpendicular, which is like an upside down T. And then we have another word for perpendicular that we like to use when we're talking about vectors. If two vectors are perpendicular to one another, we call them orthogonal vectors. So these are also known as orthogonal. It's a fun word, right? Vectors. It just means they're perpendicular. So these words meaning the same thing, making that 90-degree angle. Again, just for terminology. Okay, so we did it. Again, I hope that you like this dot product formula better than the law of cosines work that we had to do, because the work of calculating a dot product and calculating a magnitude, to me, a lot simpler than the law of cosines. But you have the option, okay? So all these things are to give you tools. You use the tools that you find most helpful in solving. So hopefully you've got enough here to get going on your assignment, but as always, if you need help, have questions, then reach out, let me know. Until next time, take care.